So LeetCode 98, validate binary search tree. So given the root of a binary tree, determine if it is a valid binary search tree. A valid BST is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both left and right subtrees must also be binary search trees. Okay, so it's a pretty recursive definition of a valid binary search tree. In this example, you can see that 1 is less than 2, 3 is greater than 2, so it's a valid binary search tree. In this case, let's see, 1 is less than 5, so that's good, but 4 is not greater than 5, and it's on the right side, so it doesn't work. So yeah, it becomes simpler once you think about what the min value and the max value for each node is, right? This number is set depending on what the parents of a child node is, right? The min and max value for 2 is negative infinity and positive infinity, right? And this is because 2 has no bounds, right? It's not the left or right subtree of anything, so it can just be any number. But starting from 1, the min and max starts changing, right? The max changes to 2 because now it has to be less than 2, and the min remains the same as negative infinity, right? On the other hand, on the right side, if we look at 3, it's like the same but opposite, right? So it has to be at minimum bigger than 2, but maximum is positive infinity. And I don't know, if we go down another one here, right? This node that protrudes to the left of 3, for instance, what would the min-max values be? Well, it still needs to be greater than 2, but it's upper bounded by 3. So it has to be something between 2 and 3. And this pattern sort of continues on and on as you recurse down down a binary search tree. And for every node, if this rule of being between a certain min and max value holds, then it's a valid binary search tree. And that's how we're going to write our algorithm. So because in our recursion, we want to pass down some extra information, i.e. the min and max values, we probably don't want to we probably want to write our own helper function, right? So we'll call it helper, right? And what are we returning? Well, what are we passing in? Well, we're passing in a node, right? We're also passing in a min value and a max value. But what are these min and max values at first? Well, we know that the root has no boundaries, right? Because it's the very first node, there is no upper or lower bound. So we can call it int min and int max. So let's get to writing our helper function. Our helper function needs to return a Boolean value. It has to it has to receive a node, it has to receive a integer min and a integer max. Right? And we're gonna need 2 cases. So we're gonna need a base case and we're gonna need a recursive case. And in our base case, it's essentially if we traverse to the very bottom leaf node of if we traverse to a leaf node of our BST with no problems, right? That means that everything above it so far has been true, right? It's held onto that rule of being of the node's value between being in a min and a max. So basically, if our node is equal to a null pointer, right? If we reach the end of our tree, then that means that we've successfully validated the BST, right? So we return, sorry, not BST, we return true. Now our recursive case, right? This is a case where we check if the current value of our node is between the correct min, it's between a min and a max value, right? So basically, if our node's value is greater than our min and our node's value is greater than our max, we don't need to do a null pointer, sorry, less than or max. We don't need to do a null pointer check because we already did that here, right? If it's a null pointer, it means that we reached the very end of our tree without returning any falses. So that means that's good, right? So in this case, right, we want to return, since like a binary search tree is only a binary search tree if the rule holds, if the BSC rule holds for both the left and right subtrees, we want to return the helper call to the left side and the right side, right? So the node left. How does our min and max change to the left, right? Well, to the min, our max changes to the new max. Our max changes to the current node's value. So as we saw in here, for 1, our max value is 2. It can't be bigger than 2, right? So, and our min is the same. So we pass in the same min, we just change the max to the current value of the node, right? And once again, both left and right needs to be true for it to be a binary search tree. So we'll do the same call, but for the right side. And for the right side, it's the same. It's just you only change the max. Sorry, you change the min and not the max. And yeah. And if this is not valid, right? If this returns false, right? Then we return false, right? And in our recursive call, since it's helper and helper, if we return false at any point, then this will be false and whatever, it doesn't matter, like one of these will be false, and that will cause the whole thing to just return false. And if we run this, we should pass most test cases. So it passes the initial super simple test case. Let's see. Okay, so it doesn't return true for int max. So it means that it's testing for really large integers as well. So then we can just use along, right? Along is just a bigger integer in C++, right? It just has a bigger min and max range. We can just replace these as well with longs and submit it. There we go. So it passed.